this problem is to write a simple DNS client. I do mean simple. You can get carried away with this, and we will in a later problem get carried away with this. But for now, all we want to do is write a DNS client which can construct a DNS query just for an A record, not for any other record type. So effectively something that can do something like this. And just prints out, the IP address. Maybe you'll get more than one IP address. Feel free to print out all of them or just one of them. Obviously, there's a lot more going on here. And if you wanted to parse more of the output and print it out, you could. Don't let me stop you. But just in order to make it a manageable kind of scope, this is our objective. Given a host name, make a DNS query and print out the response. So the point of this is to give you more practice working with sockets, to expose you to another application layer protocol. Happens to be a pretty useful one, DNS. We use it all the time. It's good to start to understand some of the details of the protocols that you might take for granted. And also, in order to do this, well, DNS is a binary encoded protocol. You need to know exactly how to pack the request bytes correctly, how to parse the response bytes. And so to do that, I guess you don't strictly need to. You could use the Wikipedia article, but I suggest that you just open up RFC 1035, which is here. It's not the only RFC for DNS, but it's the only one we'll need in this simple DNS. Did I say you could get carried away? So in this simple version, just open up RFC 1035. You don't need to read the whole thing start to finish, although, everyone needs a hobby. And if you feel like pouring yourself a glass of wine and just starting at the beginning and read to the end, I'm not going to judge. But look, there are going to be a few key diagrams that explain some of the structure of what it is that you're parsing. This is one of them. There are some others. And basically any question that you have for this exercise, you should be able to answer more or less by looking at this RFC. I really think that it's a valuable skill to be able to look at a specification, particularly if that specification is an RFC, because these are generally pretty easy to read, pretty approachable. So look at a specification and answer a question for yourself, at least about how something is supposed to be. It's a separate skill also to be able to capture packets and to observe what is actually the thing that's being sent, because not everyone follows the spec all the time. But you should be the kind of person who can read a spec. All right. So have a look at RFC 1035. Obviously, you'll need to use some of the socket understanding knowledge that you've accumulated so far. You will also need to know the IP address of a DNS server. And so I'm going to use this one, 8.8.8.8, which is a public DNS server that Google maintains. Cloudflare maintains one, 1.1.1.1. There may be others, and there are others. You can use others. But basically, you'll need a destination to send your query to that's going to give you a reasonable response. All right, so that's it. Give it a crack. I'm going to try and limit my implementation to around 100 lines of code, just a challenge to myself to not take on any of there are actually quite a few juicy kind of stretch goals. It's very tempting to go and follow them, but get the basics of the socket workflow, the sending and receiving down pat, basic encoding, decoding, and that'll really hit the objectives for this exercise. Cool. Good luck. All right, I'm going to try and make this as simple and straightforward as possible, avoid the temptation to do all the really interesting kind of edge case handling in DNS. So let's see. I've got this set up so that I can provide a host name by the command line. So first things first, let's just make sure that I can see a response to running my code. Okay, so I'll call this host name. And, I just need to encode this in a way that I can send in a DNS query. Simple. So obviously I'll need a socket. It's not so obvious what kind of socket I want. Well, I do want an internet socket, right? We're using the internet. We don't have to be using the internet. If you look further into the spec, you can see that it was 1987. They didn't necessarily know that the internet was going to dominate. And you may even be thinking, was there even a viable alternative to the internet? You can read the spec and find out. There are some actually fun alternatives to the internet that DNS does support. Anyway, we are using the internet here, and we want what kind of socket? Do we want TCP or UDP? What do you think? Well, it turns out that we actually want a UDP socket. Now, you may be surprised. You may be wondering, if DNS is reliable, don't we want DNS to be reliable? Shouldn't we be using TCP? Well, DNS queries are very small. DNS responses are small. We don't need to take something large, split it up into small segments like we do in TCP, give them different numbers, and then stitch it back together, retrying individual pieces. Retrying is very straightforward when you've only got one small message. You send it as one thing, and if you don't get a response, you try it again. You send it again. So we get retrying. I mean, if you implement retrying, it can be a stretch goal. We get retrying just by trying again. We don't need the whole TCP mechanism of sequence numbers and sliding windows and whatever. So that keeps everything simple. Now you can use TCP for DNS. It's suggested that you use UDP for basic queries, and then TCP is used for some other queries, some other messages passing, like zone transfers. Okay, but we have a UDP socket here. We do not need to bind. The operating system will always give support if we send. It doesn't make sense to send without a port, so we'll get a port assigned to us. That'll go out in the UDP header, and so we will be able to get a response. We do not need to bind. We do need to obviously send, and we're going to be sending we're going to be sending our query to 8.8.8.8. Again, you can use a different DNS server if you like. Port 53. Okay, so all we need to do is construct our query. I guess we also need to import socket. But what does our query look like? Well, how do we specify our query? We'll look at the specification to see how we specify our query. So here is the messages format. I really do think it's worth learning how to. I mean, it's not a specific thing that you learn, but becoming accustomed to reading RFCs and just getting into the kind of mental habit of reading the specification. Right, so let's go to this. Messages format here. So in an interesting design, I think quite a tidy design, the query and the response have the same overall structure, and this is it. There's a header, question, answer. I mean, these are all optional, so 0 or more questions, answers, authorities, or additional. The difference between a query and a response is there's going to be a bit to indicate one or the other, and a response is not going to have, well, a query is not going to have an answer. A response will have a question typically, because it will include the question the query that you sent. Okay, so this is the overall structure for us right now, and also when we're parsing the response. We're going to have this header first, and then the question section. So let's encode the header. And we can use this struct pack technique that we've used previously. We've got an ID. Treat all of those flags just as 1/2 int for now. Then we have a QD count, question count, an answer count, NS count, AR count. Okay, so we're going to have an XID, transaction ID, flags, 1 question, no answers, no NS, no additional. Okay, so I guess we should import struct. What is XID? XID is a 16-bit identifier why do we want something like this? Copy to the corresponding query can be used by the requester to match up replies to outstanding queries. Why do we need this? Well, we're using UDP. If we were using TCP, we will have done a handshake, and the operating system is maintaining a mechanism for associating things within the connection, the responses that are coming back to a query. We don't have such a thing. It's UDP. We just have a kind of open inbox, and if anyone happens to know the port or guess the port or spam the port that we have implicitly bound to here, then when we start receiving messages, we're going to receive their message alongside or instead of the response that we want, and so we should match up the XID. So for now, let's not bother. In fact, let's make it just some special number. 71. Why not 42? Just because that's a special number. Well, we should make this random as a kind of challenge to the server, so we don't accidentally see responses that we shouldn't in this place. Okay, so that's our XID. What flags do we want? Well, the question is going to be 0. The QR bit is going to be 0 for query. Opcode, standard query, that's all going to be 0. Authoritative answer, that's only going to make sense if this were a response, but this is a query. Truncation, not going to be relevant for the size of our query. Recursion desired. We do want recursion desired. We do want this bit to be set. What this is saying is that if the server that we're asking doesn't have the answer to the query, it should, if possible, make DNS queries itself in order to figure out the answer. Now, because the server that we're querying is not going to be the authority for what we're asking, we do actually want this to be on recursion desired. Recursion available is going to be for the server. Reserved for future use. Well, the future, according to 1987, it turned out that it was good that they reserved some bits there, because these bits are used for DNSSEC, so they are in use now, but not relevant to us. So what is the upshot of all this? Oh, and what's R code? Response code. Okay, we also don't care about that. That's where error codes are going to go. So we've got 16 bits here. The only bit of which we need is recursion desired, which 0 index 7th bit is the low order bit of this high order byte. If we're writing this as a big endian integer, that will give us 0, 1, 0, 0. All zeros other than recursion desired. All right, so here's our query. Well, it's not our query. Here is the header of our query, and it should be packed here. Let's just for now just print it out. Might as well make use of our feedback loop. Okay. Good time to pick up typos. Sure, you picked that one up. All right, so that's just what we packed. 42 turns out to be asterisks. Cool. So now we need to actually encode wikipedia.org for transmission in the query. This is the structure of a question. We have a Q name, which has a kind of encoding of a Q type and a Q class. The Q type is going to be 1 for an A record, and the Q class is going to be 1 for the internet. Again, it's fun to consider alternatives. It's also fun to consider that this is a 16-bit field. And so the designers of this spec considered that there might be 65,535 alternatives to the internet. Anyway. So we're going to put 1 and 1 in these, and we'll encode the Q name. So now we'll just do kind of placeholders. Query plus equals Q name, which we'll construct, and query plus equals, we'll just use pack again, big endian ints, and Q type 1 class 1. Cool. So how do we construct the Q name? It is not just the string wikipedia.org. because there's a kind of compression scheme that's really neat in DNS, where if you have particularly a response with lots of repeated substrings, like imagine mx1.mail.foo.com, mx2.mail.foo.com, or whatever. There's a lot of repetition here, and the repetition kind of happens from you can think of it as the right-hand side of the host name. There's a hierarchy in host names that's right to left, starting from the root and going to more and more specific things. And so it's useful to be able to say, hey, this name that I'm specifying here is either text labels or 0 more text labels followed by a pointer to an existing sequence of text labels, or pointers. You could be recursive to more things. So you could say mx1 dot and have that be a pointer to mail dot and have that be a pointer to foo dot and have that be a pointer to com, if you like. Anyway, so that's the kind of compression technique, and basically that means that the names are going to be represented as for the question, because we don't have a way to point to existing things yet, it's always going to be a length octet. Remember, networking people call bytes octets. They're just 8 bits, literally 8 bits. A length 8 bits followed by that number of octets of stuff. So for wikipedia.org, there's going to be a 9, and then Wikipedia, and then 3, and then org, and then a null. So that's what it's going to be in our Q name, and it seems kind of gratuitous to do this like Pascal string encoding of the parts of the name in the query, and it is in the query, but you'll see in the response, this will be a useful technique for being able to do a bit of compression, reuse of not only entire host names, but the labels, the portions of the host names. But for now, how are we going to encode this? We want to say, let's see, we can join this. So we can get the number of bytes as okay. So what going backwards here, since you can't read my mind. What I'm thinking is that we'll get the host name and we'll split it on dot. So now we're going to have parts of the host name. Come on. And for each part, we can treat the length of that part, so say Wikipedia, which gives us 9, or org gives us 3, as to bytes. As bytes. 1 byte. 2 bytes, 1. I also need to say that this is big endian. Again, it's useless, meaningless to have a big or little endian 1 byte integer, but that's the API. Okay, so length, for instance, 9 of the part, for instance, Wikipedia to bytes, is going to give us the byte 9. If we concatenate this to the bytes of that part, which we're going to get by encoding it as ASCII, this should give us the format that we want. 9 Wikipedia, 3 org. Okay, so make this a little bit more readable. / silence my linter. Okay, we also need a null byte. I guess I'll just tack that on here. Okay, so I won't bother printing the query since it's pretty hard to read anyway. I'm going to hit save here. Well, there'll probably be bugs, but if we see OK, then let's run it. Then there are fewer bugs. Then we'll run it again with Wireshark running and see if we can capture the query and maybe even the response. Let's see. Okay, that's good news. Let's open up Wireshark. Listen here on Wi-Fi, filter for DNS. Oh, there's already so much ambient DNS traffic. What is this stuff? iTunes? Okay, so anyway, I'm sure we'll be able to find what we're looking for. Let's put this over here. Hit send again. Hopefully we see a query. I mean, we should almost certainly see a query, right? We are sending the query, but hopefully we'll see a response as well. Hopefully it'll be correct. Let's see. No. Okay. We are capturing. It is Wi-Fi. Wait, did that come up and I just didn't notice? Yes. Okay. Thank you. So let's have a closer look at this. This is our query. There's a 42, huh? There's our XID. A record wikipedia.org. So it looks like we sent what we want, and more interestingly, looks like we got back what we wanted. So wait, let's just have a look at the query again. Here are the DNS bytes. You can see 2-byte XID, the flags, and obviously we could use Wireshark to parse this out. 2-byte XID, flags, one question. Here's the question. Wikipedia.org, type A, class internet. We sent exactly what we wanted to send. Great, we got a response. The response has the same transaction ID echoed back. That's great. The one question is included in the response. Yeah, this is going to be relevant. More ambient noise. I guess Dropbox, fair enough. The answer, I'll stop this before I embarrass myself. One answer back. The answer appears to be a correct IP address for Wikipedia. I mean, at this point, it's just up to the DNS server to give us the correct answer back. So, makes me think that we formed the query correctly. So next step will be to just parse the response. So do basically what Wireshark is doing here, given this response message back, parse it out, and we'll only print out the IP address. We'll avoid the temptation to parse everything, parse the flags, print everything out, make it exactly match dig. Look, if you want to do all that, that's fine too. But what I will do is, as the next step, just parse the response, print out the IP address. All right, quick and dirty response parsing. So we are now going to receive from. Receive from requires a max buffer size. And what we're going to get back is the response, as well as sender. I shouldn't say from in Python. I'll just say sender. And let's just print out the response for now to see what it looks like. Okay, looks like bytes. We've got our question in there. We've got the header and so on. Cool. So we will need to, in the interest of keeping this as quick and dirty as possible, we will parse the header, but more or less discard it. I mean, really, we just want the IP address, right? So ideally, we'd just skip over the header and the question. We know exactly how long the header is, so we could just skip that. Maybe, look, it's straightforward enough to... did I say I was going to keep this quick and dirty? Maybe it's straightforward enough to parse the header, so we'll quickly do that. Skip over the question and look at the answer. All right. So, what do we have in the header? We have we have a response ID. We have a QR opcode. Well, let's just call this flags like we did before. In fact, we'll call this R flags. It's not conflict. QD count should be 1 because we just sent one question. Answer count. Let's just ignore the NS count, the AR count. And we're going to achieve this by doing basically the reverse of what we did to send the query in the first place. Did I say do you agree it's a neat protocol? We're just going to say we have now these in the response. Okay, so make sure we're on the right track. let's well, we can just assert that the response XID is the same as the XID that was sent, and let's print out. This is going to be wrong because we unpack is not going to be able to unpack the whole thing. We need to unpack just the first 12 bytes, 6 half-ints. All right, we won't print this anymore. Let's see. We don't really need to do anything with the flags. Let's just ignore that. Let's assert that QD count, question count is 1, and let's actually move our OK statement here. It's clear that the assertion's passed. Okay, so we have as much really from the header as we'd like. That means next we need to parse the question. So we'll look at the question encoding. So there's the Q name. Basically, this is going to echo back exactly what we constructed. There's a Q name, Q type, Q class. And now we need to parse the Q name in the reverse of how we constructed the Q name. Again, we'd like to just skip over it, but it's a variable length. Now we constructed wikipedia.org, so theoretically we could just, we know how long it is, we could skip over it. But I say this is going to be quick and dirty. Like, there's a certain point at which you're like, if I can do it, I just ought to do it. All right, so basically what we're going to do is we're starting at an index, which is at the, let me keep this print afterwards. We're starting at an index, which is after the header. So byte index 12, 0 indexed. And what we're going to do is look in that index. Look at the response at that index. If that is 0, then we are going to break. In fact, let's add 1 here because we know we want to skip over the null byte. That's the end of our string. If not, we're going to say go forward by x plus 1. All right, so if it were org, let's say, x is going to be 3. And so we should go forward by 3, but that would get us to G. We need to go forward by 1 more. Effectively, we want to skip the prefix number by, that's 1 step, and then 3 more to skip over org. So that's where that plus 1 comes from. And if this is right, this should get us to the end. So let's check that we're doing this right by printing out now. We can print the response from 12, which is the end of the headers, to I. So this should show us 9 Wikipedia, 3 org, null. That's everything that we've skipped over. That's exactly right. 9, which is tab, Wikipedia, 3, which is does not have a special character, org, null. Okay, so that's the Q name, and now we need to skip the Q type, which is 2 bytes, and the Q class, which is 2 bytes. What am I doing? So now we should be at the response, at the answer. So let's print just a little bit from there. Let's say. Okay. And that gives us something which, well, let's have a look first at what the response should look like. It should have a name, type, class, and so on. So response, the answer, along with other things like additional records, like maybe you've got NS record or authority records like NS records, additional, sometimes glue records. They're going to have this resource record format, a uniform format. Right, and the name is there, so you might expect the name to be wikipedia.org, type and class to be A and 1, TTL to be an integer, and then for us to get to our data and see the IP address of Wikipedia there. But you don't see wikipedia.org here, and that's because of the compression scheme that I mentioned previously. In this case, this is encoding a pointer to a previous reference of wikipedia.org. So So have a look at that scheme here, message compression. So I'd encourage you to read through all of this, even though we're not going to use it. Did I say quick and dirty? But it's a very interesting scheme, and it's very well suited to DNS. The idea is that the number that we were looking at, which indicated the length of that label, like 9 for Wikipedia, instead of being a number, if the high 2-order bits are on, then don't look at the next 6 bits as a number. Look at 2 total bytes, so the next 14 bits, and have that be an offset that is a pointer within the message. So 0, 0, and then 6 bits. That's just a plain old number, like 9 for Wikipedia, 3 for org. We only need 6 bits because labels are restricted to 63 octets or less. Quite a good design. If those 2 bits are on, then you want to look at the remaining bits of 2 octets, and that's your pointer. Now, I'm not going to do that because I'm just going to try and skip over anything which is a pointer elsewhere, and look, I'll leave it as a to-do for you to implement actually parsing this and printing out the name and the answer. Good little exercise. It's recursive. You don't need to implement it recursively, obviously. You could find an iterative approach, but one label can reference another label. So if you do implement this, test it with some examples of recursive responses as well. All right, but what are we going to do? Let's have a look. At least let's do this. Let's have a look at whether that byte has those 2 high bits on or not. If it doesn't, then we should just use this logic. And if it does, then we will just skip over it entirely. So let's factor this out. Call this, look, I'm not going to call it parse name, skip name. So the contract of this will be, it starts at a given index and it returns the new index. So really we're just modifying the index in a way where now we're beyond the name, and what we're going to do is adjust this so that it handles the pointer form, not just the prefix number form. So let's just first make sure that we didn't break anything, and of course we did. So when I hit when I hit enter, we should see exactly what we're seeing. Should have no effect. Okay, was that right? No, it did do something different. Oh, I can tell. Why is it different? I can tell that this is actually the TTL, which changed between one response and another. Okay. So this is good, but what we want to do now is say if x is 0, we're at the end of the label. Even actually before that, let's do this. If x and we want to check against these 2 high order bits, so we can use an AND mask here and say OB 11000000. So if the high order 2 bits are off, what is the result of ANDing against this mask? That's 0. If they're both on, the result is going to be 1, 1, and then 0s for the rest. If one is on and the other is off, that's undefined behavior, at least according to RFC 1035, because those are reserved for future use. Okay, so if this is positive, and we can just do it like this, right? Because 0 is going to be negative, according to Python. If that is positive, let's just return I plus 2. Let's just skip over it. I mean, we called it skip name. If you're parsing, let's do this. Okay, as long as it's in a to-do, you're officially not required to do it, right? Okay. Just reading to make sure that this is right. if the byte that we're looking at right now, whenever you're adding 1 or 2 or something, your brain should be saying off by 1, off by 1, off by 1. You just need to have the constant paranoia you might be off by 1. So am I off by 1 here? No, I'm looking at a certain byte. If I go that byte, so that's like I'm at this index, go 1, 2 indexes forward, I've skipped the pointer. Let's offset here. All right, so let's have a look now, and what should happen? First, let's observe that this, because it's a C, the high order bit is on. The high order 2 bits are on, in fact. And 8 and up, the high order bit is going to be on. So C, I can see C has got an 8 and a 4 in it. High order bit is on. So this is going to be a label. Don't really care about the label value, but when we skip ahead, we should end up at this 0101, which looks familiar. That should be the type and the class. All right, so I'm doing all that to say that if I call skip name here, because we have this repetition, let's say skip name in question, let's say skip name in answer. Okay, now when we print the next 10 bytes, it should be from this, we should see 0101, if our code is right. Okay, I think that's because I didn't scroll. Okay, here we are. 0101, etc. Okay, so now, what else is in the answer? We've got a type, which is 2 bytes. A class, which is 2 bytes. A TTL, which is 2 bytes. 4 bytes. 32-bit unsigned integer. Okay, all these are things that you should, if you want the parsing practice, parse and print out. Did I say I was trying to keep this under 100 lines? I think I'm going to achieve that. I may not achieve keeping this recording under an hour, but we'll see. Okay, so 2, 2, 4, so we should skip 8 bytes. Then we get to the length, which we will need. So skip type, class, TTL. Okay. Look, it's so easy to parse. I just can't avoid the temptation to parse it. It's so easy to parse with this struct unpacking, right? We just say type. I'll say R type, so I don't use the word type. Class. I can't use the word class. R class. TTL I can say. And then RD length. And now I can declaratively say unpack this in network byte order, which is big endian, half int, int, half int. Okay. So, and this is going to be in the response from I at this point to I plus. We've got 2, 4, 6, 14. Might as well print this to make sure we're doing the right thing. And print what we're up to now, which is I plus 14. And this, I plus 14 plus RD length, the point of parsing RD length. After all of this, the next RD length many bytes is going to be our data. This is what our data says. So this should be the bytes of our IP address. RD length should be 4. And what we see printed should be a hexadecimal form of our IP address that we're looking for. Okay, we did some math wrong. 2 plus 2 plus 2 plus 4 is actually 10. And this is 10. That's me mistyping. Okay. So a record on the internet, TTL just happens to be 597 seconds. RD length is 4. And this is our hexadecimal form. Well, Python's weird way of interpreting some of this as ASCII. The non-printable stuff is escaped form of the IP address. Okay, if you haven't thought about it before, IPv4 address, the standard way of printing this out is as binary coded, as dot decimal form. So we have 4 decimals, but all 4 decimals indicate bytes. That's why the theoretical max is 255, 255, 255, 255. All right, so let's print it out that way. So let's just call this and let's print it out as decimals. So I wonder if we can use a format string for this. IP address is 4 bytes. So let's try just printing a byte for a byte in IP address. We'll kind of inch up on the answer here. It gives us a generator, which we don't want. So we'll call this, make this a list. Okay, and can we just call this string? Is that easy enough? Yes, and so let's do this. Dot join this. By the way, for Python people, I made it a generator again because join can take a generator. We don't need it to be a list. All right, so that should be an IP address for Wikipedia. Should we try that? Okay, it's not secure. That's fine. Okay, so I mean, we made the server crash, but we made the server return an error message. I know that this is because we don't have a host header on the request, because HTTP requires a host header. The Wikimedia servers don't know that this is wikipedia.org specifically that we're asking for. I mean, how would it know? Because the browser would have just sent this IP address rather than wikipedia.org. Anyway, so that's why we're getting this error message, but it is an IP address for Wikipedia. All right, so I will do a little bit of cleaning up, a little bit of refactoring. I am going to leave a lot of it to you, but let's clean up at least like some important things that you might want to address if you're at this stage. From a networking perspective, our receive from logic is flawed. This is important. So what's happening here is we're receiving one time. We're ignoring the sender. And then progressing as if the response was from the sender and a response to actually what we wanted to send. So that is to say, a response to the question that we asked. Now, we are checking that the response XID matches the one that we sent as a query, but we're sending the same one every time. So we do need to make this random, and then this assertion will confirm that server is responding to what we want. But to be thorough, we should also confirm that the sender of this message was in fact 8888 port 53, because we're using UDP. We're an open inbox. Anybody can send us a message at any time. This is also why we need to check the XID, because messages can arrive out of order. Maybe there was a delay. We sent 2 questions. There was a delay on the first answer, and we got that the second answer first or something. We're just an open inbox. We can receive messages from anybody at any time if they happen to know what port we're listening on. All right, so really, this should be in a loop. We should confirm the sender, and that's the main fix that we want to make from a kind of networking perspective. But we're going to find a few things to just tidy up as well. At the very least, we'll fix this, and we'll fix this. All right, let's fix the major flaw here, which is up here and receive from. This should be in a loop. So let's put all this here. What we want to do is say if sender is not equal to let's see, Google. Let's call this Google public DNS because we're going to use it a couple of times now. If sender is not equal to that, continue. Otherwise, we'll do everything that we were doing before and then break at the end. Okay. So really the main thing that we're looping over is this. In fact, why don't we do it like this? Get rid of this break. And if we say okay. So here we're saying loop until we get a response. Okay, actually let's make this a little better, because let's say the Google public DNS server sends back messages, well, we get them out of order for whatever reason. We actually should do that in a loop. Alright, so let's take this, let's indent this to make it part of the loop. And we're going to say if the XID will continue. If this is not, then we'll continue. Cool. We're going to continue at the end of the loop anyway, so let's do it like this. So just to check my logic, we receive a message. If it's not from who we want, reloop. If it is, then parse the header. I'll silence the linter. Once we have the header, then we'll check the XID. If it's what we want, continue to the prior logic. Otherwise, wait for another message. Receive from is just going to block, and we're going to wait for another message. So loop until we get really the response to our answer, not some other one. Right, so now I'm going to take this, call it this, and name that. Right, I should be able to hit save and see what we want. It should be approximately the same as what we see. It may be a different IP address for Wikipedia. It may be a different TTL. Okay. All right, so that's done. We don't really need to see this, and this is kind of implicit in the fact that we can print out an IP address. So one last thing to do is this. I'm going to leave that to do on line 10 for you, just because it's more involved and it's not really germane to this problem. We'll come back and do the more thorough DNS clients when we cover DNS. But let's say XID, I can use the random module randint in the range of 0, and this is inclusive exclusive, so I can just say OX, oh no, so it's inclusive, so I want to say OX FF, so random 2 byte. Integer, I guess I need to import random. Okay, So now I guess we should print out XID to see that it's different each time. Okay. All right, so I'm going to leave it there. Obviously, there's a lot more that you can do. Eventually, you could make it dig. Eventually, you can make it better than dig. And we will eventually do an exercise that is making a DNS server that's a DNS client, I should say, that's better than dig. But for now, that's it. A little bit more exposure to this application layer protocol. It happens to be an important one, DNS. We get to read an RFC. We got to read an RFC, and a little bit more practice with sockets.